All right. So when we talk about nuclear energy here in this section, it's sort of goes along with chemistry because we're going to be talking about the nucleus of the atom. Nuclear energy has to do with the nucleus. Chemical reactions had to do with what? When two elements chemically combine and have a reaction, which parts of the atoms are interacting? The electrons on the outside. Okay? When we talk about nuclear energy, we're focused not on the electrons on the outside at all. We're focused on the nucleus of the atom. Okay? So, as we know, the nucleus of an atom contains which two subatomic particles? Dylan?
Protons and neutrons.
Yeah, protons and neutrons. Protons with what charge? Positive. Now, like charges, due to the principles of electromagnetism, what should they do to each other? Two like charges. Yeah, push away, repel each other. So, protons in the nucleus of an atom should repel each other, and the nucleus should not be able to hold together based on just those electromagnetic forces. But they do hold together. And part of the reason for that is due to a special force called the nuclear force, which holds the nucleus of an atom together. And you can sort of think about the neutrons that are within the nucleus as like sort of the glue that holds together these protons that might otherwise repel each other. And so the more protons that you have in the nucleus, the more neutrons you need to keep it held together. You can't have an atom that has 28 protons and 2 neutrons. The forces of electromagnetism cause those protons to repel each other. Some elements, those sort of above 83 or so, with 83 or so protons, even adding extra neutrons cannot stabilize the nucleus. And those elements are likely to break apart and decay. So to sort of go back to what we talked about in the chemistry section, isotopes are different sort of versions of an element that have different numbers of neutrons. Here are the 3 isotopes of carbon: carbon-12, carbon-13, and carbon-14. They're all the same element because they have the same number of protons. So they're all carbon. But carbon-13 has 1 more neutron than carbon-12. Carbon-14 has 2 extra neutrons there. Some isotopes of an element are not stable. And they're what we call radioactive. They can stabilize themselves by ejecting energy or particles. And we call those elements radioactive. They're unstable nuclei that will spontaneously decay.
Would spontaneously combust?
I mean, spontaneous just means all of a sudden to do something. So spontaneously combust means something bursts into flames just randomly, suddenly. And they just have them. And when they break down, we call that decaying. When they decay, they may emit particles and energy. We have a couple types of decay that we're going to talk about. 2 types of nuclear radiation. that is released when an unstable element, a radioactive element, decays. So one thing that can be released when an atom breaks down is called an alpha particle. Do you remember when we mentioned alpha particles?
Yes.
When?
Wasn't it like with a collider thing?
Yeah, the gold foil, the collider, the Rutherford's gold foil experiment is sending alpha particles. That's when you were launching the marbles. They were alpha particles. An alpha particle is basically the nucleus of, it's the same as the nucleus of a helium atom. The nucleus of a helium atom has 2 protons and 2 neutrons. An alpha particle is a pretty large particle in terms of nuclear energy, and it can be blocked or shielded pretty easily. Just a single sheet of paper can block an alpha particle from penetrating. Another type of particle is called a beta particle. A beta particle, oh, here's how we indicate an alpha particle. With the symbol helium. 2 is its what?
Protons.
Number of protons. And 4
Atomic mass.
is its atomic mass. Beta particles is basically an electron. If an element goes through what we call beta decay, it releases an electron from the nucleus. Does anyone see a problem with this? Emily?
Electrons are in the nucleus.
Electrons aren't found in the nucleus. That's kind of weird. Okay. When we write this, and we'll talk about that in a second. When we write beta decay, what we write is E for electron. What's the mass of an electron?
0.
0. Right? It has no mass. And how about its atomic number? What, losing an electron, what charge does it have? Negative charge. Charge of negative 1. So, how does a nucleus lose an electron? Well, what happens is, in beta decay, a neutron turns into a proton. But a proton has what charge?
Positive.
A positive charge. And so the neutron loses an electron, sends it out, basically, and then it becomes a proton. And that's where that electron comes from the breakdown of a neutron. Beta particles have a greater ability to penetrate into matter. They can be shielded or blocked by a sheet of metal. They would be able to get in and through a piece of paper, for example. The third type of radiation is called gamma radiation. Gamma radiation is not a particle, like an electron or an alpha particle. It's the emission of just energy. So it doesn't have charge, it doesn't have mass, but it does have energy, and it has a lot of energy. And the energy in gamma radiation has a great ability to penetrate through substances. It can be shielded and stopped by a thick piece of lead, right? But it penetrates into substances pretty easily because it has such high energy. So radioactivity, if we think about the elements from our periodic table, it's usually, most elements that are radioactive are those with larger atomic masses. Okay. So everything you see here in light blue has a stable isotope. So almost everything you see has a stable isotope. Now there may be radioactive isotopes of these elements, but they have a stable isotope. Okay? And so you have some other elements here along the way. Okay? These are the radioactive elements. These are elements that will decay periodically, okay, that are unstable. And when we talk about radioactive elements, we're going to get to tomorrow half-life. It tells you how likely is it for this element to break down. Some atoms decay very, very slowly. Others decay very quickly. The ones in green have half-lives, which means they decay slowly, in the millions of years. And then as we go to yellow and then orange, the half-life goes from thousands of years, hundreds of years, to the most radioactive of elements, the red and purple ones, which have half-lives of less than a day, which means they decay very, very quickly. And so as we get up in atomic mass, the atoms become more and more unstable, more likely to decay, okay, and have a shorter and shorter half-life. So when we look at the strength of these radioactivity, alpha particles, like we said, the largest can be blocked just by a sheet of paper. Beta particles can be blocked by a thin sheet of aluminum. Gamma particles by a thicker piece of lead. We can measure this radiation using a tool. It's called a Geiger counter, which senses this radiation coming in. And we can sense that radioactivity using those sorts of tools. Have you heard of Marie Curie?
Yes.
Okay, she was a, of what nationality, do you know?
French.
She was French, famous French scientist. And she was very important in the initial understanding of radioactivity. So let's just watch. Well, let's watch it. Well, actually, let's watch that after if we have time. I want to make sure we get this because this has to do with your homework. So, when a radioactive isotope of an element breaks down and gives off alpha particles or beta particles, it changes. This is called transmutation. Elements change from one element into another. So, when we're writing how these elements change, we usually write the symbol for an element. What element is this?
Uranium.
Uranium, the atomic mass and atomic number. So, if we have uranium-238, which is unstable, it's radioactive, it will decay periodically. So here we have uranium-238. If it goes through alpha decay and ejects an alpha particle, what happens to its atomic number? It's getting rid of this helium nucleus. What's going to happen to its atomic number? I hear increase and I hear decrease. It's getting rid of what? 2 protons. So what's going to happen to its atomic number? It's going to go down. It has 2 less protons. What's going to happen to its atomic mass?
It's going to go up, down.
Also going to go down. But it's not going to go down 2. It's going to go down 4 because there's also those 2 neutrons in there. So when uranium-238 goes through alpha decay, its new atomic number is 90. Its new atomic mass is 234, and it's no longer uranium. It's thorium. How do we know it's thorium?
Because its atomic number.
Because thorium is atomic number 90. You need to look it up on the periodic table. Uranium decays into thorium after releasing an alpha particle. Okay? We call these things the daughter nucleus. So when the nucleus of uranium-238 emits this alpha particle, the daughter nucleus is thorium-234-90.
Why would it do so?
Because helium nucleus, the alpha particle, has 2 protons and 2 neutrons. So that's a total of mass of 4 AM.
So we have to find that out for the
All right. Well, let's think about beta decay. In beta decay, okay, we have this thorium-234-90. If it goes through beta decay, it's emitting an electron. What's going to happen to its atomic mass?
It's going to be nothing.
Nothing. Because an electron has no mass, really. What's going to happen to its atomic number?
It's going to go down 1.
Up. Up one.
Up or down? I hear both.
Up.
It's
Up.
negative.
Why up?
Because if you were going, because you're subtracting a negative number, so it'll go
You're
up.
losing a negative.
Oh, yeah.
Also, what's happening actually in the nucleus? What did we say? How is an electron coming out of the nucleus?
It's
A neutron is becoming a proton. So what's going to happen to the atomic number?
no, it's gonna go up.
It's going to go up 1. Because that neutron is now a proton, its atomic number goes up 1. And it becomes palladium, 91. So here what you see in the beta decay, this neutron turned into a proton by losing an electron. And therefore, it's a new element. If we look, carbon-14, which is unstable, okay? Carbon-14 has 6 protons, like all carbon, but it has 8 neutrons. One of those neutrons turns into a proton, okay? So 6 protons go to 7 protons, okay? And so we have 1 less neutron, but the atomic mass doesn't change. We're 8 and 6 is 14, 7 and 7 is 14. Carbon-14 decays into nitrogen-14 and emits an electron. Okay. So what type of decay is it?
Beta.
Beta decay. All right. So